In this video we have a look at arithmetic number sequences, and what makes a sequence arithmetic is that there's a constant difference between each of the terms. In this case we can see that the numbers are going up by 3 each time. So before we define a rule so we can explain this sequence, let's have a look at some basic sequence notation. We can see here that T1, the first term, is equal to 1. So the subscript in green represents the position of the number in the sequence, and we can see that T2, the second number in the sequence, is equal to 4. Now let's summarize the first 5 terms of the sequence in a table. We can see here in blue it represents the position of the number in the sequence, and the numbers in red are the actual numbers in the sequence. So the second term, which is 4, is actually equal to 1 plus 3, or the first term plus 3. And we can define that using sequence notation, saying T2 is equal to T1 plus 3. Likewise, we can see that the third term, which is 7, is equal to 4 plus 3, or in sequence notation, T3 is equal to T2 plus 3. So summarizing that, we can see that any term in the sequence is equal to the previous term plus 3. We'll put that in sequence notation by saying that Tn, so any term in the sequence, is equal to the previous term, which has got subscript n minus 1 plus 3. Now of course we can see that with these numbers that's an obvious connection. The numbers are going up by 3. But for that rule we need to define a start number so that if we didn't have the table we'd know where the sequence started from. So we say that each term in the sequence is equal to the previous term plus 3, starting at T1 equal to 1. So a rule in that format is referred to as a recursive definition. Let's have a look at another way to represent the numbers in the sequence in what's called a general form. So looking at the table we can see the numbers go up by a difference of 3 between each of the terms. And that ties in with the 3 times table because the multiples of 3 also go up by 3 each time. So to find the rule, we'll start off with an algebraic representation of the 3 times table, which is 3n. So that represents n being any number, so it could be 3 times 1, 3 times 2, etc. But of course, that doesn't match the numbers in the sequence. 3 times 1 would give us 3, and we actually want the first term to be 1. And 3 times 2 would give us 6, and we want the second term to be a 4. So what we have to do is subtract 2 from our algebraic representation of the 3 times table. So we get 3 times the position of the number in the sequence, and then subtract 2. Now this is called the general rule, and the reason why that's the case is because using this rule we can find any number in the sequence we like. We can find the 10th number or the 20th number just by substituting the 10 and the 20 into where the n is. In the previous definition, which was the recursive definition, we had to rely on a previous term. So what we're going to do is algebraically rearrange this formula, Tn equals 3n minus 2, using some factorization and some simplification. We'll then see how that ties in with some basic information from our arithmetic sequence. So first of all, what we'll do is do some factorization. We'll take a 3 out of the expression. So we end up with 3 brackets n minus 1, but we have to plus 1 to make sure it's equivalent statement. And we'll just change the order of those so we can see it with the 1 at the start. And the reason why we do that in that form is because the 1 matches the first number in the sequence, which we denote with the symbol A. And the 3 matches the difference of the numbers in the sequence, and we'll denote that with a D. For future reference, there's no need for us to go through and rearrange the equation each time to get it into this form. We can assume if it's an arithmetic sequence we can go straight to this formula and we can find any number in the sequence by using A plus n minus 1 multiplied by D. So let's have a look at how we actually do it, where we need to find the 21st term of the sequence. We'll substitute 1 for A because the first term in this case is 1, and the common difference is D, so we'll put a 3 where the D is. And because it's the 21st term we're after, we'll substitute n equals 21. Going to the brackets first, we see that 21 minus 1 is 20, and then simplifying that expression we get 1 plus 60, so our 21st term is 61. Now let's have a look at a different style of question where we want to find out which term is the first one in the sequence to exceed 185. So of course by exceed we mean the first number that's over 185. So let's have a look at our rule. We know that any term in the sequence can be found using the formula A plus n minus 1 multiplied by D. Now we know the first term is 1, that's A, and we know the common difference is 3. So what we do is we put our formula such that 185 is the actual term we're looking for. If we then go through and solve that algebraically, we can subtract 1 from both sides, and then divide both sides by 3, and we get that the term in the bracket n minus 1 is equal to 61.33. To solve that further by adding 1 to both sides, we get n equals 62.33. But what does that actually mean? Because you can have a 62nd term in the sequence, and you can have a 63rd, but how do you have a 62.33 term in the sequence? It doesn't quite make sense. And that's because this answer has actually been found using algebra. It doesn't actually relate directly to the sequence. We do need a whole number. So what we can do is do some checking, or just think it through carefully and say that if 62.33 is a theoretical answer, that means that the 62nd term must be slightly less than 185, and the 63rd term must be slightly more because the sequence is always increasing. So the first term to be over 185 will be the 63rd term.